All right, do we have any questions on alpha emission, beta emission, or any of the particles that we've talked about? I know some particles threw us off last time, but of alpha and beta emission? Okay, yeah, let's do it. All right. So the heavier elements, and you don't have to know this really, the heavier elements, anything above 82, will undergo alpha decay. Not all of the elements, I guess. I should say isotopes that has the greater mass of 80 than 82 will undergo alpha decay. And if we think about this, why is that? It has too many protons. There's so many protons when it's that massive. And so alpha decay, what does alpha decay do? It emits 2 protons and two neutrons.
Always 2 protons, 2 neutrons.
Yeah, because an alpha particle is 4, 2 He. Why not? Okay, I'm sorry.
Problem exists between computer and chair.
All right. All right. From Lost, or I don't know. I'm just kidding. All right, so 4,2 that's an alpha particle. And
4, 2.
yeah, 4. What does the 4 mean? Has a mass of 4. What does the mass number tell us? Protons plus neutrons. We have two protons. That means 2 of that mass has to be neutrons. Okay, and really the thing you have to know here is how to get the product, right? So if we start with, let's pick any old heavy element. Let's try pull up the periodic table. And really you can do this with any element you want for practice, right? Practice, the math is pretty straightforward. So let's just take radon, for example. Radon 228. And notice, that's not the mass number of radon. And that's okay. This is just a different isotope. Is this a real isotope of radon? Maybe not, right? So for practice, you just kind of just pick anything, really. And if it undergoes alpha decay, so Aman, how much mass do we start with radon? 228. And how much mass do we lose by emitting an alpha particle? 4, so what are we left with?
We have 4 minus 224.
224, that's it. So 224 plus the 4 has to equal the 228. Just make sure you double check that, especially on beta decay. This is where most people make mistakes. Okay? We start with positive 86 or 86 protons. We lose 2 protons, so we're left with 84 protons, making it polonium. Do you understand why it's polonium?
Because it's exploding.
Number 84 on the periodic table is polonium. Good? That's it. Just make sure when you're done, because sometimes we do simple arithmetic wrong in our head. When I say we, I do it all the time. So we all can do this. So just check when you're done. 224 plus the 4, is that equal to 228? 2 plus 84, that's equal to 86. And just make sure it's right. Easy to check.
Why there's a, you say that's only 2 proton to neutron, but there's a 4
What is this for?
neutron?
What does this 4 represent? That's the mass number.
Okay.
And mass number equals protons plus neutrons.
Yeah, but it's always 2 proton.
Helium always has 2 protons.
No, but everything when it's alpha.
Alpha is always
2 protons.
that. Yes, that is alpha. Don't try to, I mean, if you understand how to read this, that number right there is the number of protons, yeah.
this is the- But the masses we are not worried if it's 4, 5, 6, but the important is the proton. that-
No, this is always gonna be 4,
Always.
always for alpha,
Alpha.
always. The symbol for alpha is 4-2He. Yeah, you have to know all of the different particles, okay? And if you watch the video from last time, then I made the table of all the different particles of the nucleus, okay? So make sure you know those. You want to do a beta decay?
Yeah.
Okay. So if we take something like oxygen 18 and undergoes beta, what's a beta particle? What is it? It's an electron. So what's the mass of an electron? What's the mass number? 0. What's the charge? -1 E. That's all a beta particle is. And we do exactly the same thing. We have 18 is equal to 0 plus what number? 18 plus 0 is going to equal 18. You follow?
Yeah.
Same thing on this one. -1 plus what number is going to give you 8? 9. This is where most people make mistakes because they just do it in their head real quickly. Double check it. When you're done, if let's say you put 8, is 8 plus a negative, or you put 7, right? Is 7 plus a -1 equal 8? Use a calculator. Your calculator doesn't make mistakes if you don't put it in the wrong way, right? There's always that option too. But so this doesn't work, so that tells us that's not 7, but 9 plus a -1 has to equal 8. And if it's like, negative, stupid, okay, then do it this way. So we want to know what that number is. So we have 8. We start with 8, and this is equal to -1 plus x. Do you know how to do basic algebra? So what do? We add 1 to both sides,
Both sides.
and that gives us 9. Okay? So how should you do it? The way that it makes most sense to you. Okay?
What will happen? 18 plus 9, what kind of,
18 plus 9, what do you mean?
what is it? Is it oxygen?
That's a great question. This number right here represents what?
Proton?
The number of protons. So you'll look on the periodic table. Which one has 9 protons?
Fluorine.
Fluorine. That's how you know. That's it.
Thank you.
Any other questions before I move on? All right. So we ended with beta, right? Did we talk about positron last time?
A little bit.
We talked about what it is, but we didn't do a positron reaction, right? Okay. So positrons, what's a positron again?
A positive electron.
A positive electron. Is there such thing?
Well, apparently it's just helium all the way down, so. Sure.
But here's the thing. When you first learned about protons, neutrons, and electrons, was it weird to you? Why not? You can't see them. You've never seen one before, and it's just what it is, right? So when I say a positron, why can't we be okay with a negative electron or a positive electron, right? Or same thing with an alpha particle. Well, it's just the nucleus of a helium. That's just what it is. And why is it? Because it has 2 protons, and that's what helium is. It's just another particle that we just learned.
I don't buy it, man.
Oh, you don't believe it?
No.
You think that bunch of bullarchy?
You know,
Yeah. Okay.
it's all made up.
All right. Well, I don't know how to convince you then.
That's okay, I'm just gonna like pretend to believe and go along with it.
Okay.
Maybe it'll be true for only a few years, right?
Yeah, exactly.
Well, but how do we know it?
But,
How do we know this is what it is? Is that your question?
no, I don't really like have a question. I accept that, yeah, there's just positive electrons, but I don't like it.
All right, that's fine. All right. So if we have a proton in our nucleus, which we do, right? And we get rid of a positive electron or a positron, it comes from the proton. It's not buzzing around the atom just like electrons do because it's not negatively charged. It's inside the proton. A proton is +1. Whoops. When we get rid of a negative charge out of the positive charge, what happens? It turns it neutral. Does that make sense?
Wait, you say that again?
If we have a positive charge object, particle, and we get rid of a negative off of it, what's our total charge now? Neutral, right? And so we have 1, we got rid of 1, just like in the other problems, right? And we end with 0. We started with 1, we get rid of 0, so we end with 1. Well, it has a mass of 1 and a charge of 0. A neutron. So in the case of beta decay, then a neutron turns into a proton, right? Meaning we have too many neutrons, not enough protons with our neutron to proton ratio. But for positron emission, we have too many protons. We turn one of those protons into a neutron, and now our neutron to proton ratio is closer to 1 now. So you don't have to know. I'm not going to ask you a question, which type of emission will occur with this isotope? That's higher physics. We're not going to do that, okay? So all you have to be able to do here is basic algebra, right? All right, so that is the reaction that's going on for positron emission. So we can do an example. We have potassium 40. It undergoes positron emission. So the thing we have to know is that's a positron, right? We got to know what the symbol is. So somebody, tell me what we get. What's the mass? Still 40, because the mass of a positron is 0, basically. Not really 0, but relatively speaking, okay? And what's the bottom number going to be? What's the atomic number? 18, because 18 plus 1 is equal to 19. Yeah, always check. And that tells us this must be argon. We good?
We also breathe argon.
Yeah.
Yeah,
Not a lot, but
Not a
maybe a
lot.
little bit, yeah.
it's heavy.
Oh, that's heavy, okay. Are we good? Can we do this? So just
I am, yeah.
let it go, let it go. If we need to cry it out, do. No. Yeah, the math is easy, and that's really all you need to know for this. Are we good with positron emission? Okay. They're all basically the same thing. They just have different symbols, different masses, different charges, right? You just have to know those particles so you know which is which. Because the test might not give you this. It might say, if potassium 40, if I say potassium 40, what does that mean?
Okay.
It means that's the mass number of potassium. How do we know that number? Oh, we look on the periodic table.
That's 39.10, but you rounded to 40.
No, This is an isotope. Why is that 39.10? That's the average of all of the isotopes of potassium. This is one specific isotope. All isotopes will not undergo decay. Will not. Some of them do, some of them don't. And we don't have to know which ones do, which ones don't. We don't. We just have to be able to predict the product, what we get. What we're left with after alpha decay, after beta decay, after positron emission. Good? So it says it undergoes positron emission. That might be the question. What's the product? What's the final product? That's our answer, and this is how we get there. Does that make sense to everybody? How we do these? Any questions so far? Okay. I don't have a worksheet for it. I don't know what happened. I guess I must not have printed them out for you. I have to take a quick break. Sorry about that. So think about that. Practice. Pick one on the periodic table and practice.
That's my problem.
But the last
It was hard.
And it's just straight.
if I got, for example,
Yeah, I think you have to pause. You just have to pause.
but the important for me is important certain you have to give a good grade,
Not physiology, I gave you.
So
Yeah.
this.
You can retake it.
but if you pass,
You have to have.
So then
but I
you'll
have
know exactly what is great. This is like after the and then you'll just write that equation out, but it really.
Really makes you think.
I found this whole thing.
Give me a little one all of a sudden. I didn't realize they get like swollen all over. It's weird.
I think through that means what we have.
All right. Any questions before we continue? Okay, let's continue. The next one we deal with is not a emission or decay. This one is an electron capture. All right. So an electron capture, if we have a proton, and this time we're capturing an electron, we're taking it in, that means it's one of the reactants. You with me? It's not a product anymore. Emission or decay is a product that emits off of a particle. But the capture, it's electron capture, so we're taking in an electron. Now where's this electron coming from? the inner shell of our atom. So this is the outside of the atom, but not the very outside, not the valence electrons. This is the electrons on the inner shell. Okay? So we have 0, 1, negative 1e, so that's an electron. And we do the exact same thing. This time it's on the left side instead of the right side. So we start with a mass of 1, we get rid of 1, we get rid of 0 rather, and we're left with 1, right? We start with 1 proton, or a positive 1 charged nucleus, and we get rid of a negative 1 charged nucleus. Sorry, we don't get rid of it. We add a negative 1 charged nucleus. Makes this what? 0. So it's another way to get a neutron. Do you have to worry about how we determine which way it has to get the neutron? No. Okay? And again, it does this so that it can make that neutron to proton ratio closer to 1. Question?
No, sorry.
Okay. All right, so we do an example. We could do these all day long, guys. They're all the same. Doesn't matter. You just have to remember which particle and which side, because this is an electron just like a beta particle is, right? But this time it's on the reactant side. And what do we get? Can you do this yet by yourself?
197 over 79.
And that is, oh, I don't have Krista here, so she can't tell us. Gold. We good? But it's just the same simple equation over and over again. How are we feeling? Can we do this?
Always 0, negative 1, the electron is,
Well, electron has a mass of 0
yeah,
and a charge of negative 1.
always.
Always, yeah. From day one of this course, that's what it was, and that's what it still is. But when it's a positron, then it's a positive exponent, positive charge, right? Still E, but okay. Well, maybe we could just pick another symbol for it. You guys want another symbol? No way, right? Just know it's a positive electron. Good enough? Any questions about electron capture? Okay.
Sorry, did you say that's part of, like, that's considered an energy created reaction?
I put it down there, but they all create some energy. They all do. Okay? And in fact, we didn't talk about gamma yet, did we? We talked about gamma, but let's do a gamma one real quick. If we have carbon-14, for example, and we emit gamma, what are we left with? Carbon-14. Nothing happens, right? So that will not happen by itself. Now, a lot of times what happens is a beta particle pops off too. And we get nitrogen-14. But we also get gamma coming off. That's the energy. Okay? Can that happen during electron capture as well? Sure. Can that happen during alpha particle as well? Sure. Right? So we're not going to just have one that just has gamma radiation. It'll come with the other type. Does that make sense? And so electron capture, it's not an emission, so we put it with the rest of them. Does that make sense, Andrew? So it doesn't. We're not going to use electron capture to get nuclear energy. We don't use it for that. But can it give off energy? Yes, and it does. Okay. All right. So the next one, now we're getting into the energy producing reactions. Nuclear. These ones are the cool ones, guys. fission. Okay, nuclear fission is when we have two smaller isotopes. Sorry. One larger isotope that breaks apart. Now, it doesn't just spontaneously break apart. We have to shoot a high-speed neutron at it, and then it'll break apart. So we have to make this happen. So this is man-made nuclear energy. Well, not man-made, but we have to initiate the reaction.
Artificially triggered.
Yeah. So when one larger nucleus is bombarded, I don't know if I spelled that right, with high-speed neutrons, to split into two smaller nuclei. So that's basically a bullet where you're shooting at the nucleus to get it to split. If you don't shoot it with enough energy, it's not going to split, right? And so we have nuclear reactors. In fact, anybody scared about nuclear energy?
Big fan.
This is the future, ladies and gentlemen. Okay, in France, and this was a long time ago, so maybe this statistic is different now. Was 85% of their energy or their electricity is produced with nuclear energy. Have you heard of any problems with France and nuclear problems? No. And so one bad thing happens and somebody tries to scare everybody into not having that. I don't know why. But where do we get most of our electricity, guys? Coal. Has anybody ever died from coal? Oh, lot more. Well, that's because we use it more. But if you don't follow protocol, if you don't follow the rules and the safety protocol, bad things are going to happen, right? Even on the highways, bad things happen when you don't follow the rules, right? More people die on the highway than nuclear reactors, so we shouldn't freak out about it. We should just make sure we follow the rules. That's all.
Did you know we're getting a plant in Utah?
Are we?
Yeah, down in Delta by our coal plant.
Oh, heck yeah. Like a large plant?
I don't know.
I heard we was going to start getting more of them in America, but I wasn't aware of that one.
Yeah, and I think, I don't know, there's some existing nuclear company that's testing a small modular reactor in Idaho. It's about the size of a
Uh-huh.
semi-trailer.
Yeah. Cool.
I'm heavily invested in nuclear. You guys should be too.
No, this is cool. And as soon as one of you guys figure out a cold fusion, then we're rocking and rolling.
Like,
Too late?
Germany, some country came out of left field and just like smashed the fusion record.
Oh, did they?
For a sustained reaction.
Oh, I am off on my news here. Heck yeah. So yeah, if we can get fusion, that's even more. I'll even show you a chart if you want. It's not on the exam, but if you don't want it, I'll just not talk about it. Okay. So that's nuclear fission. So here's an example of a nuclear fission reaction. So not all isotopes are fissionable. Okay. The heavier ones, not all heavier ones are, but this one in particular, uranium-235. And how do we get it to go through fission? We throw a neutron at it. So 1, 0, N, right? And we get, now I have to give you something. I'm not going to say, okay, now what do we get? That's not enough information. So I might give you, okay, 91, 36. This is one of the fissionable isotopes that we end up with. Plus something else, plus what else do we get? We get more neutrons. Krypton. Yep. We get more neutrons. What happens with those other neutrons? They hit other uranium-235 isotopes, and it splits those ones. And they produce more neutrons, and it splits those ones, and those ones, and those ones. We call this a chain reaction. And you got to have that chain reaction for fission, because if you just have one of these guys, okay, great. This is not enough energy to do anything, right? And what we do is we have this, not always, but a lot of times it's in water. It heats up the water, and the steam comes off the water and turns a turbine. This is the same way we produce electricity from coal. We burn coal, we heat water, and turns a turbine, and it generates electricity. So that's how we get energy from it. So I'm going to say plus O, we're getting a lot of energy with this, okay? A lot more with fusion we'll talk about in a minute. Okay, so can we do this mathematically? It's exactly the same, just now there's more components. So maybe we should write an equation. Maybe be a little bit easier. So we have 235, I'm getting that right there, plus 1 equals 91, plus, we can call this x, y, and z, right? We're looking for that guy. Plus x, plus, there's 3 neutrons. 3 times 1 is 3. Does that make sense to everybody? And then we can add like terms. So that's plus 94, right? And subtract 94 to both sides. And this is 236. What?
Plus 3 plus 94.
3 plus 91 is 94. I just added those together. You follow? And so we subtract that and we get 142. So that means in this isotope, we got 142 on top. Well, now we got to do the bottom. 92 plus 0, we don't have to worry about that because it's 0, is equal to 36 plus, we can call y, plus 0. We don't have to worry about that because it's 0. So we subtract 36 to both sides, and we get 56. And 56 is what? On a periodic table is barium, right? Yeah. Good? That's all you have to know, ladies and gentlemen. You don't have to know how a fission reactor works. You don't.
Okay, what class do I take for that, though?
Nuclear, well, you can learn it in nuclear particle physics, but that one's kind of intensive.
I want the theory, not the math.
Probably just physics.
Okay.
I don't know if, you might want to look, let's see. Because the high school physics, I don't teach it, because I teach it in high school chemistry. But it is a physics concept. Probably take a nuclear engineering class.
Yeah.
You'll for sure learn it there. No. And you'll learn more of the ins and the outs, and maybe those particles will make sense if you, I don't know.
So it's left 56.
Yeah, does that make sense how we got that?
But I didn't see 56 on the top.
Right here? I was doing the bottom numbers. This is 36. So 36 plus what number is 92? 56.
56 says the Y.
56 is this bottom number. These are just random letters. I didn't have to use X, Y, and Z. I can use whatever. Okay?
And the top one was X.
Yeah, I solved for X here and I got 142. Does it make sense how I got that?
Oh, that's good.
Okay. Do you want to do one more?
Yeah.
Okay, let's do one more. And I'll try to be a little bit more, I'll write it a little bit different so that maybe it's easier to see. Okay? Okay, so maybe we get plutonium. Let's see. Oh, that's not on this periodic table. Let's see. Plutonium, let's say 248. I don't know if that's a fissionable one. We'll just 248. And plutonium is that 94? 94. Yeah. And so on, if I give you one of these, I'm going to have to give you the whole equation because there's just so much you have to know. It's just not just, okay, it undergoes alpha decay and it does this, okay? So, and maybe, let's see, 1, 0, and we get, let's say, zirconium 97 plus something else. And this time we only get 2 neutrons. So is it always going to be 3, always 2? Maybe sometimes it's 4, right? All right. Let me write these equations a little bit slower and nicer and neater. Sorry, I kind of just rushed through it last time. Here we go. So we're going to start with the top number. Let's just deal with the mass. Law of conservation of mass says we start with 248 and we add a neutron to it. And that's going to equal to, does this make sense so far? A 97. And I'm going to just put X, Y, and Z here. X is the mass number of the isotope. Y is the atomic number of the isotope, and Z is the element symbol. You following? I can use A, B, C. It doesn't matter. Okay? And so I'll say plus. We're dealing with the mass, so I'm going to say plus X plus what? We have 2 neutrons. Each of them have a mass of 1. So that's going to be plus 2. You follow? Because there's 2 of them. Okay? And let's simplify it. 248 and 1 on this side makes 249. Equals 97 plus 2 is 98 plus X. Do you understand that step?
97 plus 2 is not 98.
Sure. Come on.
19.
You're right. I was just making sure you guys are with me, that's all. Okay. I know how to do plus 2, guys. I'm just kidding. All right. So here we go. You understand how thanks for pointing that out. Okay. So you got to be careful. Even I make mistakes. I probably make more mistakes than you guys, so just be careful. So now we got to solve for X. So what do, Amon?
Minus 99.
Minus 99 both sides. And we got our X is equal to 249 minus 99. What's that? What is it? 150. So in our isotope, we can change this X to be 150. Good? Now let's check the atomic number, or the charge. So we start with 94 plus 0, we don't have to worry about that, is equal to 40 for zirconium plus Y, we don't know what Y is, and 2 times 0 is still 0. So that's it. So we subtract both sides by 40, and we get Y is equal to 54. So we can change this Y to be 54. And what are we going to change the Z to be, guys? Xenon? You follow? All right, so that's nuclear fission, and that happens on the Earth. We make that happen on the Earth. And what else do we use the fission stuff for, that we should never use it for? Atomic bombs, okay? Now, should we worry about nuclear fission reactors blowing up? No. They won't. The way they're set up, the way that they won't, okay? The most it'll do, and the most it's done, is get too hot and it melts down and all the radiation leaks out into the environment. So that was the bad thing, and then it makes the whole city maybe, you can't live there because it's too much radiation, but that's happened, what, 3 times in the history of when we started it? Okay? So, I don't know, maybe it's gonna happen in Utah now that they have them. Just kidding. No, we should be good. As long as dedicated, what do we call them, competent workers are there, right? Then we should be fine. Shouldn't have a problem. And we don't have earthquakes in Utah. Well, not big ones anyway, right? Well, wasn't it a tsunami that caused the one in, or maybe it was an earthquake in Japan? Yeah.
Earthquake, 'cause they built it like on a fault line.
Yeah, so, yeah, just, I guess there's a few fault lines in Utah, but they're,
Well, I mean, not in
yeah, that's a good place to put it. No, I was kidding.
Delta, nothing in Delta.
All right, we good on fission? Okay, let's talk about nuclear fusion. Nuclear fusion. So this happens in the sun and the stars. And in Germany, I guess, right?
In China.
China, okay.
There's a few.
Oh man, I better do some research. I'm back on this. Okay. Telling everybody, yeah, we don't do this yet, but okay, maybe we do.
Yeah, no, it was a sustained reaction for like 17 minutes or something like that.
Huh.
Yeah, and then there's like, I don't know, I was reading about it,
And sun and what?
if they can get a sustained reaction for I think it's like 36 minutes, then we should be able to just like contain it.
Huh.
So we're close.
Well, all we need is a little bit of villain in us, and we like Doc Ock. So Doc Ock from Spider-Man, he actually had sustained fusion, and it was gonna wreck the whole everything, right? He made a whole sun right there. Okay, a little science fiction, but
Aren't fusion reactions a lot safer? Because if it goes wrong, like, it just stops.
maybe, I don't know. The sun
Google
doesn't.
told
The sun doesn't stop, thank goodness,
Well, that's a sustained reaction, right?
because it produces enough energy to keep it going, and that's the hard part. That's the hard part from day one. How do we get enough energy to keep this thing going?
Insane amount of gravity.
So-
Stops.
Anyway, it comes from the sun and stars. So this is when we have 2 smaller nuclei. Fuses, that's why we call it fusion, into one larger nucleus. So we take big elements on the periodic table to get fission, and we take small elements to get fusion. And not all isotopes will make fusion, not all isotopes will make fission.
To one large.
So an example of this would be, let's go to Doc Ock. He's still tritium, right? Well, he first was given the tritium, and then he went evil, and then had to go steal some more. And this is not very much of all of the hydrogen, but thank goodness hydrogen is the most abundant element in the universe, right? Plus deuterium from the ocean, we can extract deuterium. And then these guys come together, and what do we get?
Wait, did you mean to write 2 H's?
Yes.
Okay.
Yep.
Why?
Why?
Yeah.
Because we take 2 small elements, and this is what's going on in the sun right now.
Right.
But these are isotopes, right?
Yeah, these are two different isotopes of hydrogen,
Okay.
tritium and deuterium. The majority of hydrogen is just
Wait,
H1.
Sorry, that's, I think what I'm hung up on. Why are you calling it that and not?
Oh, deuterium?
Yeah, yeah.
That's just a special name we give it, because it's,
Make it sound.
we can call, yeah, we can call it H3 and H2. That's fine.
Okay, yeah.
Yeah.
So that's what it is, and that's
Yes.
why you wrote two H's.
Yep.
And used different words. Okay.
And
Okay.
anybody know what we get when we fuse these things together? We have to have enough energy, so I'm gonna add energy over here, because we have to have enough energy to get these things to come together, because if you throw two positives together, what's gonna happen? Zhong, 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 right? They're just gonna repel. But if you have enough energy, enough speed, they'll come together and then they'll fuse together. Okay? They'll hold strong, and then you have that nuclear strong force that holds it together. And we'll get what? We start with 3 and 2, so what mass do we end with? 5. You with me? 3 plus 2 is 5. 1 plus 1 is 2. What element is this? Helium, right? Yeah. So in the sun, when the sun first began, whenever it was hydrogen, mostly hydrogen, if not all hydrogen, and it fused together. So, do I know this for sure? No. But fuses together, and now we get helium. And now hydrogen can fuse with helium and get what? Lithium. And so on. And it does this until it gets iron. Iron is iron's too heavy to fuse together with something. So it will not sustain fusion with heavier elements. And I'll show you a little graph that kind of explains this. And again, you don't need to know this. All you have to know, guys, is how to determine the product. So should I quit with the mumbo jumbo and just get on with it, or what? Okay. Plus a lot more energy. We wouldn't have to give energy if we didn't get more than, right? Otherwise, the sun would just run out of energy and it would go away, and the stars. So that's an example of nuclear fusion. Any questions? You want the chart?
Okay, good.
Okay, so this is mass per nucleon. You remember what a nucleon is? The protons and neutrons, okay? Not just talking about just protons or just neutrons, it's all nucleons. And then here you have the atomic number, or the number of protons, right? So down at the bottom we have 1. This is hydrogen. Its mass for the hydrogen proton is much greater than all of the rest. So we said all the protons are the same. They're not. For chemistry, for chemical reactions, yeah, we keep it basically the same. And if you're talking about 1 proton, it's not that much different, right? But it is different, okay? So its mass is way up here. And then you take iron, number 26 on the periodic table. Its mass is way down here, and this is not drawn to scale. And then way over here, uranium, number 92 on the periodic table. It goes up a little bit. And so we get a Nike swoop. Ish. That was a little bit off. Right on. Okay. So we get something like this, and this is not exact, but okay. These guys right here have a possibility of undergoing fusion. These guys over here are fission. Now, not all of them, right? Okay. And now let's think about what's happening. So if we have two hydrogen atoms that fuse together, they make, and again, I'm not drawing this to scale, I'm just doing this on purpose so that we can kind of see what's going on. And really, This graph looks more like this. So let's do it that way. And so the mass of a helium nucleon is right here. The mass of a hydrogen nucleon is right here. Well, what happened to that extra mass? You can't just destroy mass, right? You ever see this equation? There's that mass. That mass is converted, well, it's high speed mass. It's converted into energy. So we get a lot of energy right here for fusion. If we do this with fission, so this breaks into maybe this one and this one, for example. So we started with this, and we ended with, and I didn't draw these to scale for sure, a lot less energy than fusion. Because this curve more goes like that. I kind of drew that wrong, okay? But that amount of energy, or that amount of the mass that's lost, is converted to energy the same way, but it's a lot less energy than fusion. So fission, a lot of energy, but fusion, a lot more. Hence, it's happening in the stars, in the sun. Good? Any questions on fission and fusion? Do you want another example? Yeah? And I don't know if this is a real fusion reaction, but we'll just do it for practice, right? Okay, what do we get? What's the mass number of our new product? 8. And what's the atomic number of our new product? And so what is our new product? Beryllium. Okay? That's all you got to know how to do, guys. So we've been talking about all this energy, nuclear, and all that stuff, but that's it. It's not a ton you have to know. Any questions? Okay, we already talked about gamma radiation. Any questions there? Okay, another thing that you should know is penetrating power between alpha, gamma, and beta. Alpha, beta, gamma. What does it mean to penetrate? To go through something, right? So which one do you think has more penetrating power? Alpha, beta, or gamma? Gamma, because it's smaller. Yeah, it's tiny. In size, relative size, it's basically nothing, right? It goes through a lot of things. Now, it's not visible light, so visible light only goes through transparent materials, right? But this high energy gamma ray can go through relatively thin lead or light, right? But if you get thicker lead or concrete, it still goes through a little bit, but it stops most of it. And that's why Superman can't see in lead buildings, right? Well, he's X-ray, but okay, whatever. So the penetrating power for gamma is greater than, which one is the next strongest? Alpha or beta? Why beta? Because it's smaller than alpha. What's a beta particle? Just an electron. What's an alpha particle? 2 protons and 2 neutrons. We can call it helium, right? Okay. So beta is next, and then alpha. These are just the Greek letters, so we can write it out. Gamma has greater penetrating power than beta, has greater penetrating power than alpha. Does that make sense in our mind? So alpha will be stopped by a piece of paper. That will stop alpha. Well, even this, right? It's just a piece of paper. Will stop alpha. So alpha actually comes from the sun. We're getting alpha, not a ton, but we're getting some. And doesn't affect us because it can't go through our skin. But if we ingest it, then what? It can't get out. So be careful with that.
Don't eat sunlight.
What?
Don't eat sunlight.
Yeah, don't eat sunlight. No, it's not sunlight. You get a small portion. If you get one, and it's not going to do anything, right? But so the count, if you get a Geiger counter and stick it in the room, it'll have a low count of radiation. But that's not hardly going to do anything. But if we're around if we're working in a nuclear reaction, we're working at a nuclear reactor, then there's probably going to be more of that. Like, you guys ever heard of Marie Curie? She's like the famous woman scientist that got a Nobel Prize and stuff. Well, her work, she worked with a lot of this stuff, and she ended up with cancer because she was around this radiation all the time. But if just on a day-to-day basis, we're fine. Okay. All right, so alpha stopped by paper, beta stopped by thin metal, like aluminum foil even. And then gamma has to be thicker lead or concrete that will stop it. Will slow it a lot down anyway. So don't be around gamma unless you want to be like Loki. He's a bad guy. Okay, I'm just kidding. Sorry. We good? That's it. We're done. Any Yay, what are you talking about? I'm just kidding. Any questions on nuclear reactions or even acid base? Anything?
I have acid base questions.
So nuclear's not too bad, right? You do have to know the different particles and this penetrating power stuff. But yeah, not too bad. Okay. Oh, we're not done. We are not done. Yeah, we are not done. That was the easy part. Ready? I don't know. This is the best part anyway. Okay. Oh, I'm sorry. Oh, I just burst your bubble, didn't I? Okay. Man, it's a good thing I flipped that page. Like, what the heck? Okay. Okay, sorry about that. Any questions on nuclear reactions? All right. Now, these nuclear reactions happen. Why do they happen? I'm not talking about fission and fusion. I'm just talking about the decays. Why do they happen? So that the unstable isotope or the radioactive radioisotope, will become more stable, right? Okay. So we're going to learn about how they do this, what the rate is. So we talked about the rate of nuclear reactions don't change, right? We can't give it energy to get it to speed up. We can't put it in the freezer to cool down or slow down. It's just going to be what it is. And this brings us to half-life. Anybody ever heard of carbon dating?
I was just about to ask that.
Half-life of penetrating power?
No, this is a whole new topic. So we go to a tree or an object, and scientists will determine how much carbon-14 it has to predict how old it is. What do you think? Very, very accurate or inaccurate?
I think they say that is carbon-14. They measuring the carbon-14 has a long, staying longer, like a nuclear, like atoms, particles.
Yeah, it stays in the substance, but over time, it decays just like everything else, all other unstable isotopes,
They were
right?
looking for carbon-14
Yeah, they're looking at carbon-14. So what they do, and I don't know the ins and outs of it, but to make it simple, what they do is they determine how much carbon-14 per molar per mass a substance has, right? And then they take something that's new, and they say, oh, how much carbon-14 is in it? And depending on how much it has, they can say, okay, it decayed this long, so we can figure out how old this is. And dinosaurs are millions and millions of years old. The Earth is billions and billions years old, 4 billion, right? What do you think?
Inaccurate.
Yeah.
Every time I see it, it's like a huge range.
Yeah. Now, it's under the assumption that the ratio of carbon to carbon-14 has always been the same. That's a big assumption in my mind. So carbon-14, carbon dating, I don't feel is very accurate. But we can use this with other isotopes, and this is kind of their process of coming up with the half-life of carbon-14, which is a huge number, 5,370 years-ish. For anybody ever been around that long? You have? Oh yeah, okay. So a big assumption, and so I don't believe it's something that we should say this is what it is, okay? We should look more. Figure's a better way to do it, is my opinion, okay? So half-life is the time it takes for half of a given substance to decay. And when I say substance, it's going to be a radioisotope, right? Because if it's not a radioisotope, it's not going to decay. So I'm going to just say T1/2 is my symbol for half-life. I don't know if this is the book's symbol, but okay. And there is a formula that we can use. You guys ever take college algebra? Math 1050? Okay. And you do an equation like P equals AE KT or something like that. Remember this? Should we use it? Should we use this formula?
There's something else I want to know.
No, let's not. Okay? And the way I'm going to show you, I mean, you can definitely do this, but it just seems like it makes it way more complex for what we're using it for anyway. Okay? Maybe if this was our field, we'd want to get the exact maybe we'd use that math, right? So for us, we'll just say, okay, let me just show you an example of what half-life is. So after one half-life, we have half as much left. So if we start with 10 grams, so for example, we start with 10 grams, after one half-life, then let me just say 0, we have all of it, right? At time 0, we have all of it. And so we have 10 grams at time 0. After one half-life, however long that is, different for every isotope, then how much are we going to have? 5 grams. Do you think we'll have exactly 5 grams? This is a probability. And that's why I think this right here, it's just a probability anyway. So this is just making a prediction. Let's make a prediction simpler. And if we're going through like 30,000 half-lives, yeah, this would be easier. But in our class, probably maximum we'll do is 10. Okay? So after 2 half-lives, we have half of half. So it's gonna be half of 5. 2.5 grams. You with me? And then after 3 half-lives, it's a half of half of half. We just, another half. It's like the probability of getting heads 3 times, right? What's the probability of getting heads 3 times in a row? Is it just half? Is it just 50%? No, it's 50% of 50% of 50%, right? And so the probability goes down the more half-lives happen. So it's going to be half of what we started with, half of that, it's going to be 1.25 grams. Will we ever get to 0? Theoretically, we won't, but will we? Yes, right? If you take a handful of pennies and dump them on the table, and you take out all the heads. Heads are good, heads are good, heads are good. Get the tails, dump them out again. Okay, take out all the heads are good, because they decayed, right? And you keep doing that, would you eventually get rid of all the pennies? Yeah, you would. It's just a probability, okay? So it's not exact here. You with me?
So if I let the penny out long enough, it would turn into helium?
No, it'd turn into a tell. I'm just kidding. I'm just... All right, so let's do a few examples of what you might be asked. And there's really only 1, 2, 3, 4 possible examples, questions I can ask you. 4 possible questions. But it's the same process in all 4. So here we go. Do we understand what half-life is? Okay? So strontium-90 has a half-life of 28.8 years.
It's
Strontium-90.
What is T?
This is the half-life, T1/2. Okay? And this is just the way I'm going to write it out, okay? It might read half-life, but okay. Are we good? So if we have 500 grams to begin with, and it is stored, we want to know how much we have left after being stored for 85 years. Okay? So maybe we won't check it. Maybe the next people in our
Years?
whatever. Okay?
It's 28.8 years?
28.8 years. Yep. All right. So here's how I start this every time. At time 0, how much do I have?
500.
500 grams. That's when I stored it, right? So I start with 500 grams of this isotope. And then, I want to know how much I have left after 85 years. So what can we do? How many times are we going to cut it in half? What? How do we figure this out? Yeah, divide. The total amount of time divided by 1 half-life, right? Every time we have 28.8 years, we have half as much as we started with, right? So we're going to do 85 divided by 28.8. And these are years, right? So if we put our units cancel out. And actually it's not. This is years per half-life, right? So years cancel out, and the half-life goes to the top, so that's going to give us the number of half-lives. So again, we can use dimensional analysis to help us to know what math we got to do. So 85 divided 28.8 is like 2.9 something. We'll just say, okay, that's 3. About 3 half-lives. So we're going to cut it in half 3 times. So after 1 half-life, how much do we have? 250 grams. After 2, we have 125 grams. After 3, 6, 2.5. Is that right? All right, yeah. So we're gonna have that many grams after 85 years. That's, what? That's something we can definitely do, right? Would have to have several different people maybe.
But it says 28 years
28.8 years.
half-life.
Yep, that means after 28.8 years, we're gonna have 250. Okay, then we're gonna go another half-life, another 28.8 years, and what's
Until
that?
get to 85 years.
Yeah, that's right. Does that make sense? Yeah,
So in this case, because we rounded to 3, we're able to do like 3
yeah.
half-lives, right? But if we do end up with a decimal, we can't really round like 2.7, and how would we do that? Or would we still just round to the nearest whole number?
It'll always be simple. For this class, we're gonna keep it simple. Good? And if you didn't, if it wasn't simple, we'd have to use this. We're not going to have to use that. Well, that's not the exact equation anyway, but anybody want it? I could probably think about it and come up with it, but I don't want to if I don't have to. Does anybody want it?
I think it is what you wrote down, except I've seen it as instead of P, it's
It's
A
what-
sub 0 or something like that.
Yeah, it's
It's like your original amount.
where A is 1/2, but yeah, it's pretty close in that form, yeah. All right. Does that make sense? That's our first example. How to determine how much we have after a certain amount of years. You okay with that? Questions? Is it blowing our minds?
No, but this is all just breaking down into helium?
No.
Okay.
All right. Remember, helium is one of the other products that we don't care about. All right, it's just floating up in the air. It's probably going in your mouth, so be careful. He starts talking with a high voice or something. No, I'm just kidding. All right. Example 2. So I'm gonna keep it basically the same problem. So this time, we have 62.5 grams left after 85 years, right? Same problem, but this time we want to know, so again, the half-life is 28.8 years. We want to know what? How much did we start with? So 85 years ago, how much did we have? You with me? We're going to set it up exactly the same way. At time 0, that's what we're looking for, right? How many half-lives have happened? It's the same numbers, right? There's going to be 3 half-lives. We'll take a break after this. So we're going to have 3 half-lives. Well, how much do we have after the 3rd half-life? You with me? Everybody understand how I got these numbers? So we have 62.5 grams. But how do we go the other way now? Right here, we divided by 2, then divided by 2, then divided by 2 until we got to that, right? So what do? We multiply by 2, and we get 125 grams. We multiply 2, we get 250 grams. We multiply 2, and we get 500 grams. Oh. Do you follow? So it's the same process. This time we're just multiplying instead of dividing, because we're going backwards. Any questions on how to determine how much we started with? Okay. You ready for a break? Or do you want to just keep going? Your call. This is the last thing. For real this time. All right, I'll take a break. Does anybody want me to show you how to use this formula? Anybody want a formula? Okay, let me show you. And if you don't like it, well, don't use it. Do it the way I showed you. Okay, here we go. So AT is the amount, I don't know if maybe it's not T, maybe it's F, maybe we should call it F, is the final amount, right? And A0, or AI we might call it, is the initial amount, the starting amount. And that's in, it could be grams, it could be moles, it could be atoms even, right? It doesn't matter, just amount of substance. And then we got our half because we're going to multiply it by a half and raise to the y power. That y represents the number of half-lives. So, okay, we can figure out the number of half-lives just like we did. We know the starting amount. If we know the initial amount, maybe we're looking for the initial amount, we can figure this out, right? Or maybe we're looking for the starting amount. Okay, then we just do a little bit of algebra to solve. So let me do it with this one. So this is our starting amount, 6.62.5. Multiplied by a half, and we did it 3 times, raised to the 3rd power. So that's going to give us, what do you think it's going to give us? It should give us 500, right? You do the math, try it. If you want to try it this way, that's the formula that we use.
This is the times 1.5 E.
Yeah, this is multiplied by 1/2, raised to the 3rd power.
The formula, times 1.5.
Yeah, times 1/2
And
Good.
to the power of 2.
to the power of y, where y is the number of half-lives. So if you want a formula, there it is. I mean, this formula works great until you have to solve for that guy. Right? Once you have to solve for that guy, logarithms, right? And most people, especially if you're going into nursing and you don't want to deal with all that stuff, right? That's why I don't teach it that way. But you could. Definitely could. Are we good? Did we get 500? What did we get?
I just know
Oh, wait, maybe I did it the wrong way. So I don't use this formula. Let's see. Yeah, this is actually the initial amount, and this is the final amount. I think I had it flipped. Yeah. So this is, we're looking for that, and this is 62.5. And that's another reason I don't like formulas. If you remember it wrong, you're out of luck, right? But either way, the math works out the same. You're still doing math, okay? All right. Ready for example 3? So far, we learned how to determine how much we have after 85 years. We want to know how much we had at the beginning, 85 years ago. And this time, we want to know, I already did that one. We want to know how much time has passed. So if we start with 500 grams, and we end with 62.5 grams, We know those values. And we know the half-life is still 28.8 years. We want to know how much time has passed. Are we good with what's going on in this problem?
Time?
Yeah, time. T, so this is T1/2, that's the half-life. So we're just looking for how much time has passed to go from here to here. Good? So I set it up exactly the same way. At time 0, how much do I have? 500. I don't know how many half-lives I'm going to have because I don't know how much time has passed. But I know at the end I'm going to have, so at X amount of half-lives, I have 62.5 grams. You with me? How are we going to figure out what this number is? Once we have that number, we can know how long, right? Because each half-life is 28.8 years. If it's 5, we multiply the 28.8 by 5. If it's 2, we multiply it by 2. Does that make sense? Okay. So how can we do that? How can we figure out that number right there? Divide by 2 until we get there.
How many times you can
That's right. That's right. We do it one time, we get 250 grams. Divide by 2 again, our second time, we get 125 grams. Divide by 2 again, oh, that's our third time, we get 62.5 grams. So that means 3 half-lives have passed. So 28.8 multiplied 3 is going to give us around 85 years. Does that make sense? Do you see how it's the same process every time? You're just maybe going backwards or finding something a little different? How we feel? We'll do a couple more examples that aren't with this example. But let's do one more example, one other different type of question I could ask. Unless you have any questions up to this point. No? All right. So this time, so example 4. We want to know what the half-life is. How long is it? So that means we know the initial mass is 500 grams, right? And we know the final mass is 62.5 grams. We know what the answer is going to be because I'm using the same problem, right? What?
What is it?
The initial mass, right? So, and I can write it different, right? I can say how much this is starting, right? And this is ending. And then I know a time of 85 years has passed. Okay. So now what? Do the exact same thing. At time 0, how much do we have? 500 grams. So many times later, again, we don't know how long a half-life is, so we don't know how many. That's going to give us 62.5. Well, we already figured out that it's 3, right? The same way, right? We can either divide, this time we can multiply. We can multiply this way until we get to 500, right? You can do it either way. So we find we have 3 half-lives. So 3 half-lives is equal to what? 85 years. You with me? So we divide 3 this time. And that's gonna give us 28.8 years. Am I freaking you guys out, or how you feeling? Yeah, that's because we rounded the whole time. Remember, when the number of half-lives is 2.9 something, it's not gonna be exact. We good? Should we do a different example that's not this 85 and 228.8?
Yeah.
All right. But those are the 4 types of questions that I could ask you here. I'm not going to ask you 4. I'm going to ask you 1 probably, or maybe 2, and you'll have to be able to do it. Okay, so let's do this. So let's say we have gold 198 has a half-life of 2.67 days. So we know that 14.5 nanograms of gold 198 is used in a body to treat leukemia, for example. Leukemia. We want to know how much will remain after 8 days. So we got to do this treatment maybe every week. We want to know, okay, how much is going to be left in their system after 8 days, right? And does everybody understand the question? So we're looking for the final mass, right? Do we have to change nanograms into grams? No, we don't. We just want to know how much, right? We start with nanograms, we're going to end with nanograms. We start with kilograms, we're going to end with kilograms. Okay? So what do? Yeah. How much do I have at the beginning, guys? 14.5 nanograms. Okay. How many times am I going to cut it in half? Do I know? How do we figure this out?
2.67 divided by 8.
Or is it 8 divided by 2.67? Well, let's see. Let's make sure we know. Let's do 2.67 days per 1 half-life, right? Divided by 8 days. What is our answer going to be measured in? Per half-life. Do we want to know how many per half-lives we have? No, we want to know how many half-lives. So we're going to flip that. 8 days divide 2.67 days per half-life. Right? So now days go away. It's divided by a per, flips it over and makes it, we're looking for half-lives. Does that make sense? So 8 divided by 2.67, what is that? About 3. So we're going to cut this in half 3 times, and this is what we're looking for. Right? So 14.5 divided by 2 is 7.25 nanograms. Divide by 2 again is 3.567. 3.6, what? Maybe. What is it? You guys have a calculator, use it. 6, so 7.25 divided by, it's not 6, what does it do? 3.6, what, 25? And then we're gonna divide it by 2 again and get,
That's 1.881.
so there's our answer. That's it. How you feeling? Can you do this?
Maybe like do example 3 and 4, just this one, because this was basically example 1 with different.
Yeah.
numbers, right?
Yeah.
So I don't know why 3 and 4 didn't make as much sense as 1 and 2.
Okay. So let's see, the next one says, how long? Should we do how long it'll take?
Yeah.
Okay.
Another one is
So yeah, let's do another example. So this time it says thallium-208. Does it really matter what isotope it is, guys? No. Okay. Has a half-life of 3.053 minutes. How long will it take for 120 grams to decay to 7.5 grams? So we're looking for how long will it take?
minute.
Either minutes or seconds or hours or months or days or years. Well, yeah. Should we use minutes? Yeah. Half-life is measured in minutes. Let's use minutes. And if it asks how many seconds, then what? We convert it, right? If it asks how many days, we convert it. How many hours, we convert it. Okay, so where do we start? Yeah, how much do we start with? I always start here. We start with
208. No,
120 grams. 120 grams decays into less, right? Because we started with 120 grams. So yeah, it doesn't tell us you start with, right? But you kind of have to read the whole problem to make sense of it. And we end with 7.5 grams. So what do? We divide it by 2 until we get 7.5. And count how many times we divided by 2. So our first one's going to be 60 grams. Our second one's going to be 30 grams. Our third one is going to be 15 grams. And our fourth one is going to be 7.5 grams. Does that make sense? So it takes 4 half-lives. Well, if one half-life is 3.053 minutes, how many is 4 half-lives? Right? Well, what's that going to give us? Yeah. Can you do these? Not too bad, right? You have to think. And if you just don't want to think, guys, well, I'm sorry. You just got to think. One more?
Yeah, can we do the fourth example again?
Yeah, let's see. So we want to know the half-life. This is the one you want to do, right? The half-life of iodine 131. We want to know what that is. If we start with, so the original amount that we start with is 50 grams. And the amount that we end with is 6.25 grams. And the total time that elapsed is 24.3 days. So what do? At time 0, I have 50 grams. At some other time later, some other half-lives, we have 6.25 grams. So what can I find? Can I find X? How many half-lives have passed? Divide by 2. So after one half-life, we get 25. And maybe I won't give you one that's a beautiful, easy, nice number, but just use your calculator, right? And after 2 half-lives, we get 12 and a half. And if we divide it by 2 again, we're going to get 6.25. So this is 3 half-lives. Is our answer 3? No, because that's not the question. Our question is, what is the half-life? How long is the half-life? So what do? Yeah, we got to do something with 3 and something with the total time, right? What do? 24.3. Multiply 3 or divide 3? Divide, right? Does that make sense in your mind? You have to think about it for a minute, but okay. Divide by 3, and then let's just put our units here. This is days, and this is 3 half-lives. That's going to give us how many days per half-life. And that's what we want, right?
So the original information is saying that after 24.3 days, 50 grams had decayed to 6.25
Yeah.
grams.
Uh-huh.
Yeah, I was confused on that first.
Are we good then? So we do that, and we're going to get what? Close to 8.1 days is our half-life. How we feeling? Doing okay? Okay, that's it. That's all I have for you. Period. No more. We're done. Woo!
We're still doing test review on Tuesday though, right?
Yeah. So, does anybody want to stay the last 40 minutes and ask questions today? Because here's the thing. The review on Tuesday is for the final. Are we good? So is everybody okay taking the test either today or Monday? Does that not work for anybody? Doesn't work? Okay. Does anybody want to stay after class on Tuesday to take it? Uh-huh. Exam 5. The final is going to be, so I found out that I can't be here on Thursday. So I told you maybe I could be here on Thursday. So if you're going to take the final, you need to take it in the testing center. Okay? So the testing center is, you can take it, I think, did anybody look at the schedule for that? What did I put?
I think I could take it until next Friday.
Yeah, are they open on Friday?
Yeah,
Are they?
I'm taking my test tomorrow.
Oh, maybe the final they are. Okay. So you have Wednesday, Thursday, or Friday to take the final? Not Friday?
I don't think it's Friday.
I thought Fridays were closed, but
Fridays are open actually.
oh, it is open for final? Okay.
Because it's on Fridays.
Okay. Yeah.
For Tuesday, would we just take out our laptop and sit here?
Yes. If good.
Can I just take it Tuesday?
Yes. If you want to take exam 5 on Tuesday, but here's the thing. We probably have to start a little bit before class ends so that you have enough time, because I have another class at 2 o'clock. So if we started at 12, that would give you 2 hours to take the exam 5. So if you still want to take it in the testing center, do it. Okay? Okay, who's all coming on Tuesday to take the final after class? Okay. So a few of you? Yeah?
Wait, sorry, 5, right?
Not the final, sorry. Not the final. I'm sorry. Exam 5, you can either take in the testing center today, and is it open?
It's open Friday and Monday.
Okay, so you could take it today, Friday, or Monday in the testing center. Exam 5. If one of those days does not work for you, I will also allow you to take it starting at 12 o'clock, maximum. We got to start at 12, so you have 2 hours after class on Tuesday. We good? So, your choice. I'll be here anyway, so I don't need to know how many's coming. Just, if you want to take it on Tuesday, you can. Okay, and then the final exam, you got to take in the testing center. I think I have it for Wednesday, Thursday, Friday. Wednesday, Thursday, or Friday. No. Yeah. And again, if you're good with your grade after exam 5, oh, we're done. I don't know, maybe that's not a good thing. Maybe we should make everybody take the final. I'm teasing. All right. So, any questions about the schedule or, yeah,
How many questions is on the final?
like between 70 and 80. Between 70 and 80. But listen, that's a good thing, because then if you miss one, it's not 5% dog, right? It's like closer to 1 or 2%. So I think you have 3 hours on the final. Yeah, 180 minutes. Yep, 3 hours. And unfortunately, my other job starts on Monday, so I have to skip on Tuesday to be here for you guys. But then, I mean, students aren't back, but I have to go back. Are we good? Yeah. Okay, do we have any questions on anything for exam 5? I mean, we can spend time on Tuesday for exam 5, but then we won't have time to spend it for the final. So I'm thinking today, if you're good, you're welcome to leave. Okay, yeah, thank you.
But yeah, like on the homework, on the, once the chapter's in introduction, that's basically.
Do you have it there? Yeah. Let me know.
Okay, so it says chapter H3O plus, aqueous following OH- 5 Celsius.
So what information are we given? Yeah. Because everybody's happy that we're out of classes.
Okay, so like what I was really confused about.
Okay, it says calculate the concentration of H3O plus. That's basically the concentration of H plus.
And that's why.
Okay. Aqueous.
No, not these two. Because these two sections were the same. I was just dividing by 1 times 10 to the negative 14.
Do you care if we do this for everybody that's
Yeah,
here?
no, we can probably do it.
Okay. So if,
Because it was like,
oh, you want me to do this one or
each
the other
one
one?
they're the same, and I don't understand why.
They're the same answer?
Same formula. I was using
Yeah.
1 times 10 to the negative 14 on.
Okay, I'll
find
show
the
you.
OH and-
Go ahead and flip it back to the other one. Because I already kind of started that one. Of each aqueous solution with the following OH concentration at 25 degrees Celsius.
So
Okay.
another 25 Celsius doesn't mean anything.
Yeah. So we have NaOH. The concentration of NaOH is 1.8 times 10 to the negative 2 molar, right? So we want to find the concentration of our H plus.
Right.
Okay. So if anybody else wants to know, I'm doing another problem. So we're going to start with what we know. 1.8 times 10 to the negative 2. I'm going to change that to be moles of NaOH to 1 liter of solution. Does that make sense?
Yeah.
Okay. And so here we got to find H plus. So let's take a look at our reference sheet. Okay, so we're looking for H plus. How do you find it? Oh, we can find it a couple of different ways. Are we going to use this one?
No.
No, we don't have enough information for that. So we have this one right here. H plus concentration is equal to 10 to the negative pH. That means we have to know the pH. Okay? pH is this. No, that's not going to help us. Right here. So pH plus POH equals 14. So if we want the pH, we have to know the POH.
Right.
And POH equals negative log of OH minus concentration. And we don't have the OH minus concentration exactly, we have the NaOH concentration.
Right.
So we got to convert this into the OH. And how do we do that? There's one of those for every one of those.
Right.
It's a 1-to-1 ratio, so basically it's the same thing. Does that make sense?
Yes.
Okay. So now what we're going to do, POH is equal to negative log of 1.8 times 10 to the negative 2. Are we good? So let's figure that out.
This is you're going to post it online too.
Yeah, I'm recording this. Yeah. Yep, so if you want to go, you're welcome to go. So we got log of 1.8 times 10 to the times 10 to the 2 negative. And then we have to do a negative of that. And we get 1.74. That's our POH. That one's done. Now we can plug it in here and subtract POH from 14. So 14 minus 1.74. So our pH is 12.26. Is this making sense to everybody? Once we have the pH, now we can plug it in this formula and find the H plus concentration. So 10 raised to the negative 12.26 raised to the 12.26 negative, and that's going to give me 5.50 times 10 to the negative 13.
Okay, so you got the same answer. You just took so many more steps to get there. Because for literally all of these, I was just dividing by 1 times 10 to the negative 14.
Okay.
And like in the homework guide, she was just like, this is where it is. I have no idea where that number came from.
Okay. This is the way of doing it without logarithms. If you want to use logarithms, we can use that number.
She didn't use the logarithm. Oh, here, I'll show you the video.
I don't care about the
Okay.
video.
I'm so confused. Like,
That's where that number comes from. Because the scale is 0 to 14. But this is the taking the pH and making it into whole numbers. But if we put it, and I would have to think about it or look it up to find out. So it's 1 times 10 to the negative 14.
so like we did that for NaOH, but like why would it be the same for aspirin? Milk of magnesia.
The same number?
Yeah, and then
Because it's the same pH scale.
right.
And I don't like,
I mean, this is all the same too. Just the 1 times 10 to the negative 14.
do you understand that?
No.
Then don't do it that way.
Okay, we hear way so much harder.
Is it?
I think so. Yeah.
Unless you go on, it's like, okay, I'm just doing this random crap for nothing. Does it do you any good?
That's how I feel a lot.
Doesn't
About
do,
a lot of this
doesn't do us any good. Now, if we have this, and I guess you don't have this, do you?
No. At least not readily available.
Teacher, are you staying at the class? I will have a question come back.
Okay.
Please come here. Come back.
Well, it's better if you do it during class, because class isn't over yet.
No, yeah, I know, it's just oral.
All right, so, yeah, we start with this. And we're going to this. So we change it to OH. Negative log of OH. And the reason I'm doing it this way is because you have all of these.
Right.
I can give you some magic number and say, just use this, guys, and then what's gonna happen?
I'm gonna remember it wrong. Not know how to apply
Yeah.
it like I do.
Yeah.
Apparently. Okay, seeing it this way makes a lot more sense.
So that's basically what we did. We did negative log, we found the OH, it's the 1-to-1 ratio. Negative log of ROH got us the POH. 14 minus the POH gives us the pH. Then 10 to the negative pH gives us this.
Right. And then so these
So it's
ones
really
where
only
you're finding
3
which
steps.
go in the other way. Okay.
And I could probably try to come up and
With the magic
thank
number.
you, and explain why that works, but I'm a little rusty with that way. So, but it has to do with the logarithms. This whole thing is logarithmic math.
Right.
Unless, if you want to use logarithmic math, then we can. Or we can just use these formulas.
Okay, yeah. I like your way better.
That you
now
don't have
that-
to memorize it.
Yeah, that makes sense. I just need to like draw that on my hand before I go.
Just practice drawing it. Practice drawing it, and then on the test, well, you can draw it right there.
Yeah. Yeah, I got scratch paper. That's a good point. Okay, smart guy.
Well, I don't know if I'd say that, but
I don't think I have any other questions.
I just like to use what we have to solve it. And that's weird, she'd have you do it that way if she gives you these. Yeah.
No, I'm
So in
good.
Canvas, the exam is taken out automatically, or you're gonna take it?
No, I will not take it out of Canvas. So after I figure your scores, I will email you your final grade.
But I'm happy with what I have.
Then you're
Don't
good.
take that fine.
Yep,
That's what I.
yep.
So that's-
Yeah, so you can know if you're good with your grade.
After example.
Yeah. Yeah, what's your question, Mariana?
In the word pH and buffer,
Okay. In section 1? Section 3. Which one?
the last one, the hot, what volume of
Okay. Yeah, I'm going to do one more if anybody else wants to be involved with it.
the titration.
Okay, so this says what volume?
I guess the word that threw me off is titration.
Okay. That word titration means what? It neutralizes. A strong acid neutralizes with a strong base and becomes salt and water. So we can write that equation, and when it says that, that tells us we have to write an equation so that we can know if it's balanced and what the ratio is. Okay? So you want me to do this whole problem?
Write the equation.
Okay, so yeah, let's do it. It says, what volume of HNO3, and it has a pH, titrates with BaOH2. So here's our strong acid, here's our strong base. You with me? So we're going to have HNO3 plus BaOH2. And this is just this is a neutralization reaction. If we write the products, what are the products? This is the double replacement reaction. HOH or H2O, right? Plus barium nitrate. And if we write the chemical formula for barium nitrate, barium is in group 2, so it's 2 plus. Nitrate is NO3 minus, right? Cross the charges and we get BaNO3 2. You have to write it correctly, otherwise you're going to balance it off, right? Does that make sense? Okay. So
To do this on the test, we'll have a question.
that's a great question. I gave you a study guide. Look what it says.
I'll have to bite.
But you should know how to do this. I would say yes, know how to do this. And if you don't have to do it, it'll be better for you, right? But know how to do it, and you'll be set. Does this make sense? Is the hard part knowing what the chemical formula is?
No. I think I was just, because we didn't really go over the titration that much. And then I saw this and on the homework too. Did we go over titration?
I probably talked about it.
Talked about it, but
So titration, do you guys do a titration lab?
we just did.
Like we just did yesterday.
Yeah, and so what did you do there? What was the purpose of that? To calculate a certain concentration, right?
Yeah, yes.
But so titration, when it reaches that equivalence point where you get the light pink color, do you remember that? That means it's neutral. That means all you have in that solution is salt and water.
But if it turned dark pink.
Then you went too far. Then there's no way, then
There's no neutralization.
then it's not neutralized and your reaction doesn't make any sense. Even if I write the chemical formula, it's not right. But if we say we titrate it, that means we reached equivalence point and it's perfect. And when we do the math, we're assuming, okay, it's neutral. Good? So then we balance the equation. We're going to have to put a 2 right there and a 2 right there. And we have it balanced, right? Okay. So now that we have that, should we do this problem? Okay.
Asking for volume.
So we have this has a pH. So this substance has this solution has a pH of 1. pH equals 1.07. And it titrates with 15 milliliters of a 0.012 molar concentration of barium hydroxide. And so what's the question? The question says, what is the volume? So we're looking for volume, milliliters or liters. So we'll just say liters, okay? On the test it might say milliliters, then you'll just have to convert it to milliliters, right? All right, so we want the volume of this solution. Are we good? Okay, so we're looking for this, and we know everything for this. That means eventually we have to get to moles so that we can do the mole-to-mole conversion from our balanced equation, right? Does that make sense? So we're going to start here. And do you have this chart?
I do.
Okay. If you have it and you have it on your little reference card, I'm not sure. I can't tell you that it's going to be on there because I think the department has a specified one, even though I send it to them. But so this just tells us kind of where we are and where we're going. So we know everything about this, right? Or actually we know this. You following? So from here, we want to do the mole to moles because we're going to something else. Does that make sense? So we can take our molarity and we multiply by our volume. Make sure our volume is measured in liters. So we got to convert that into liters. And then that's going to give us moles of BaOH2. Then we use the mole-to-mole ratio here. It's a 2-to-1 ratio to get to moles of HNO3. Once we have moles of HNO3, in fact, since we have a pH here, we might have to do some more stuff, right? We have the pH. We can go this way to figure out the H plus concentration. It's a 1-to-1 ratio, so that's basically the molarity of that. So it looks like maybe we don't do this way. Maybe we don't have to do that. Maybe, let's see. Let's just see. So pH, 10 to the negative pH gives us the H plus concentration. So basically it's a 1-to-1 ratio. So we have our concentration of our acid. And we're looking for volume. We've got to do both of them, yep. So yes, we do have to. How do I know? Because I have moles over liters, and I want liters. This is what I'm looking for. So if I have moles per liter, and I have moles, I can cancel it. So if I have moles of HNO3, I can do so many moles per 1 liter of solution. This is my molarity. Are you with me?
Yep.
So yeah, that's kind of a big problem, isn't it? We have to start here and go this way until we get to here. Start this way and go this way until we get to here. And then we can kind of put that together to get liters. Yeah.
Sorry, can I ask where we got this question from?
This is from the worksheet that I didn't give you guys.
Oh my,
Oh, hold on a sec.
We have the acid
It's here.
bases.
Oh my gosh.
Oh,
I checked before class and I didn't see it. You guys want this? No, it's not this one that I checked for. It is on campus, yes. In every other class, you have to create your own. So you're welcome. But if you want that, I'm sorry.
Yeah,
But I-
Mine online.
But I did not print it out for you on the nuclear. I apologize. Okay. So should we do this problem? Because it's a big one, right? All right. So we're going to start with what we know. We know this guy. We know most of that guy, right? So we have 0.012, and I'm going to write it as moles of BaOH2 per 1 liter of solution. You with me? Okay. And then I have volume, but it's in milliliters. It's section 3, the very last one.
Oh, thank you.
And so now I got to change milliliters into liters. I can do that right here, or I can do that somewhere else. Do you know how many liters is 15 milliliters? 0.015 liters. Right? Okay. So from here, we get the liters to go away. And now we have moles of our substance that we don't want. We want a different substance. So we're going to use the mole to mole ratio. In our balanced equation, it says 2 to 1. So we're going to do 1 mole of BaOH2 to 2 moles of HNO3. You following me? Good? So now what? So we can calculate how many moles. Do we have the volume? No, we don't. So we can't continue on that mole roadmap that way. We're kind of at a block.
You changed the 15.0 milliliter
To liters.
to liters.
Uh-huh.
Like 0.0.
Yeah. Yep. And so we do this. Let's calculate this. And we get 0.012 multiply 0.015 multiply 2, and we get 0.00036 moles of HNO3. So that's not our answer, but okay, that's something that we have. So I didn't have to start here, but it's something that I need. So there's my first step. First answer that I need to get my answer. Yeah.
sorry, the 2 to 1 moles is just because we already wrote the equation.
Well, yeah, I had to write that equation.
Okay.
Do you know how to come up with that equation from this problem?
We'll get there.
It says it titrates. That means it's a neutralization reaction. We have a strong acid and a strong base. It's a double replacement reaction, and this is what we get. And then you balance it. Okay? So you may be given the balanced equation, or you may not be given an equation, period. Make sure you can do either way. Okay? And then we have the pH of our acid is, what is it again? 1.07. So from there we look at our reference sheet. From this we can calculate what? The H plus concentration is going to equal 10 to the negative pH. And so we do that. 10 raised to the 1.07 negative, and we get our OH concentration is 0.085 moles of H plus to 1 liter of solution. Molarity, right? Okay, but that's not what we want. We want acid of HNO3. So what's the ratio of HNO3 to H plus? One of those to every one of those. Can you see
The
that?
other one was 2. Okay, yeah.
There's only one. We're not using the balanced equation here. We're just using this formula. For every one of these compounds, we only have one H.
Oh, okay.
Are we good?
Yeah.
So 1 mole of H plus to 1 mole of HNO3. So moles goes away, and this gives us the molarity of HNO3. So we can calculate that, which is a 1-to-1 ratio, so it's 0.085 molar concentration of, keep writing H, HNO3. That also is not our answer. So we have two things. So here's our second piece that we need. You following? And then we have moles, and we're looking for liters, right? This is moles over liters. So we have liters. So we can either start here or start here. Which one do you want to start with, 1 or 2?
Start with 1.
Okay, sure. And
Because it has the volume from the beginning.
yeah, that's the question. What's the volume?
Also then, the moles and moles are cancelled.
Yeah, so we have 0.00036 moles of HNO3. And here we have 0.085 moles of HNO3 to 1 liter of solution, because that's what molarity means, right? Moles goes away, we're left with liters. Hallelujah. Or we can change it to milliliters, right? If the answer is looking for in milliliters. But here it doesn't say, so we'll just leave it at liters. And so we do 0.00036 divided by 0.085. And I get 0.004 liters. Maybe I should have it in milliliters because that's way tiny, right? 4 milliliters. Does that make sense? It's kind of it is a big thing, but you just have to know what you know, start with what you know, and move until you get to what you do know. If you come to a roadblock, start with another known value.
So every time it asks for neutralization or titration, we add that extra step?
You have to write the equation. If you don't have a balanced equation, you can't do chemistry.
No, I mean, this additional step of having to do different.
No, not necessarily.
No,
Not always.
not always.
Mhm.
Hard to tell which one.
Okay, don't memorize what you do. Use dimensional analysis until you get what you need. So let me just kind of run through this again. I started with what I knew, right? And I used the balanced equation, and I got this. And then I can't do anything else because now what do I do with that? I have moles. I want liters. I don't know my molarity yet. So then I come over here. I start with my other known bit of information until I have molarity of my concentration. Once I have molarity, now I can put those together to get my volume. So a lot of students say, just tell me how to do it, right? And in a math class, say, okay, when I do this problem, I just multiply, I just cross and multiply. I cross and divide. I multiply and divide, and then I get my answer, right? Maybe that's an algorithm. If you want an algorithm, then it has to be a certain condition. And then you have a different condition, you have to have a different algorithm. A different condition, you have to have a different algorithm. You're going to have to memorize 59 algorithms to do this concept. Or you use dimensional analysis and you go, you start with what you're given, you cancel stuff out, and in this case, we come to a roadblock, so we had to start with something else that we was given.
That, I know how to do that dimensional analysis.
Yeah.
Like I can solve it just by reading it, you know? Like,
And-
what's it asking for? What do I start with?
Yeah,
But then this one, like, I wouldn't know how to put it together. Because mostly you can just do
did you
one
see
little
that I didn't know how to put it together at first? Did you see that?
or-
You have to use your thinker. And I know that doesn't make it easy. It doesn't. And this was a really tough problem. It really was. You just have to make sure you use your units and make sure you end up with the unit that you're looking for. Use your mole roadmap to help you, to guide you. But
So it gives you a lot.
that was a rough problem. It was.
Can you scroll up and show us on the mole roadmap again, exactly like?
Yeah, let me
what
erase
the
this.
look like? Yeah, that'd be great.
All right. So here, we was given the concentration of our base. And we was also given the pH of our acid, right? We can't go this way, because then that gives us something we already know. We can't really go this way, because that gives us something we already know. So we're not going to follow that path. So we can either start here or start here. Doesn't matter. You always start with your known information, your given information. So what can we do? And in reality, can we try this way? Sure, we can. We can try going that way, get POH. Then we get a pH, like, hold on a second. That's the wrong substance,
That's when I would kick myself.
right? Then we say, okay, don't do it that way. We come over here, okay. I take my molarity, and if I want to go this way, I'm going to multiply volume. Do you understand why we multiply volume? Moles over liter, multiply liter, gives us moles. Oh, now I'm here. Now I use my mole-to-mole ratio for my balanced equation to get me here. I want to get to here anyway, because it's asking for the acid, right? And then, well, this is what I'm looking for in the end. Maybe I do that a different color. This is what I'm looking for. That's my question. So I got here from this side. Now let's start here and go this way. 10 to the negative pH. That gives me this. Since it's a 1-to-1 ratio, it's the same as that. If it's not, you have to convert it, right? If it's a 2-to-1 ratio, then it's either going to be multiplied or divided by 2. And how do you know which it is? Dimensional analysis. And then once we have our concentration, we have moles over liter of our acid, and we have moles of our acid. Oh, that's going to cancel.
Pause. So I just, that last step, that we had to use the stoichiometry basically, right?
Uh-huh.
Is there like,
It's not on here.
I was gonna say, but is it always involved in that step?
If you're going from pH to an acid, yes. If you're going from POH to a base, yes.
And that is just the ratio of the molecule or whatever.
So in this case, we have HNO3. We're dealing with the acid. We found H+. We have how many moles per liter of H+? Well, in this one, we have 1 mole of H+, because there's only a 1 right there. Yeah.
within the compound.
Yeah, so we don't use the balanced equation here.
Okay.
And there's, for one of those,
Also, we calculated really strong acid like H2, that's what you have to multiply.
that's right. So in this case, it's a 1-to-1 ratio, and if you see that it's a 1-to-1 ratio, do you have to even do this? No, you don't. So that goes away, and now we have moles per liter of our acid, which is our concentration. And we want liters, so now we can just flip this, right? So that liters is on top.
Cool. I guess I've never realized we can ask for steps between like volume, like it feels like we've always looked for like moles or grams or
Uh-huh.
molarity, but yeah, I mean, I know we've looked for volume before, but it's just interesting.
Is it because it's more treated as like an intermediary step here? It's like, how do we get that as our answer?
Yeah.
So don't, this is kind of, the mole roadmap is kind of a crutch.
I need it, yeah.
And if you need it, you use it.
Yeah.
But can you run and jump with a crutch? Maybe not, right? You might have to, okay. I'll have to I'll have to get up those stairs a different method,
Yeah.
right? I'll have to whatever.
Right. Okay. And, okay, cool. Also, I think it might
Did you have a
just be
question?
good to know, so,
You're just here to learn? Good.
I think it is good to know that like on the last exam, and I've just noticed that when you click exam, like it will show you the thing that they give you, and it doesn't have the pH side of it, it's just like the thing, so I don't know if we
Yeah.
should mention that on Tuesday, but.
Yeah, I did say that I think they're gonna give you this one without the pH part.
That's right, okay.
So if you want that, you better put it on your little reference card,
Yeah, okay.
okay?
I think I mostly got my answer there, because it's all about pH, so I feel a lot better about the nuclear chemistry of anything.
You'll be here Tuesday, right?
Yes.
Oh, but then that would be too late. Have to take it Monday.
The exam 5, if you want to take it in class, I'm offering you to take it after class on.
I have my lab
I have no idea.
right after.
I want to.
Or I would take it.
You have it right now, or just on Tuesdays?
Just Tuesdays.
Okay. Yeah.
And that's why I'm taking it today, because on our lab,
You're taking the test today, aren't you? Oh, we got to get started then. Okay. All right. You want to sit up here?
because in our lab, they have, he's making us take an exam as well.
Okay.
Does it not have the pH
I just wanna take it today just for the
What?
Band-Aid.
sheet that you're gonna
I was
use?
like,
Um, do you, let's see.
well, that's also because like what's on that treated worksheets messages.
Do you have one of these that's blank?
So,
If it's not blank, I can't let you use it. But it's, you passed it. You passed it.
Oh, no, I have another copy.
I know, I saw it in there, you passed it.
and you already don't have a lot of time to study, so it's like whatever I'm gonna be doing, I'd rather be counting towards something.
But yeah, that's, I guess, why I was frustrated, because I did the homework.
Thank you.
Thank you, good luck.
So, it is what it is.
I know, I think it's just some of the problems.
Right there.
It's just weird things too. Or
Oh, no?
like forget where to
Oh.
go when doing dimensional analysis. It's like, oh, I've got my units now. I'm lost.
I saw it in there. Thank you, take care.
Appreciate it.
Good luck.
See ya.
Right there. Oh, no. Back. That's right.
No.
Okay.
Can I erase it? Or doesn't matter? And can I use this part? Can I use this one? Oh, okay.
So if you do well on this, and then you don't have to take the final? That depends on what grade you want, right?
Rebecca, I mean, either way, if I do the final, it'll just keep me to a B plus.
So here's the thing with the final. And most people who take the final don't do well on it. And some people do. The reason they don't is because they didn't study it all the way through. They don't have it down, because you have to know everything now.
Yeah.
So if your best chance is to do the best you can on this one, and then if your grade is if your grade is, let's say, a B plus, and you want that A or A minus or whatever, it is possible to get an A, but you'd have to get an A on the final. Does that make sense?
Yeah, because my lowest one is the first exam was like a 55. So I have to do better than a 55, right?
Yep,
Better than a 55.
that's right.
But what are the odds that there's just 70 questions?
Yeah.
I just
So
wanted to get over this because they have the chem lab and then I have